The topic is the basics of center of mass. We'll start with, first of all, why do we need the concept of center of mass? And to understand the reason why we need center of mass, we'll go back to Newton's law of motion. But the basic purpose is related to Newton's law of motion. So Newton's law of motion in the form force is equal to mass into acceleration is strictly applicable for a particle. But we have been applying for objects like shown in the screen. Even for the blocks like this also we apply Newton's law of motion, though this is not a particle, but its behavior is similar to that of a particle. Let's understand why. If we observe any particle on this block B, and for illustration we have taken two particles on the block B, one is shown in blue color, other is shown in red color. And if the block undergoes displacement, if we observe motion of these two particles, what we find, both of these particles will have identical displacement. So not only these two particles, is true for every particle on block B. So every particle on block B will have same displacement, and if the displacement are same, velocity and acceleration are also are same. And this kind of motion is called translation motion. And this is a particle-like motion. Every particle of the object have same displacement. So not only for particle, we can apply Newton's law of motion even to objects which are particle-like. But let's take another example. In this case, we imagine a uniform rod. It is placed on the smooth surface at rest. Either you can imagine placed in the smooth surface, or you can imagine this rod is placed in the space, and if force F is applied here. After we apply this uniform force, what kind of motion or what way the rod would move? Try and visualize the motion of the rod. So if you look at at a point little later, this is how the rod may appear. What we notice, the rod which was vertical has changed its orientation, and different particles on the rod will have different displacement. On the top, lesser magnitude of displacement, bottom greater magnitude of displacement. So though the object is one, different particles have different acceleration, whereas Newton's law gives one unique value of acceleration. So question is, how do you apply Newton's law of motion? So it becomes impossible to apply, or it becomes invalid for this kind of object. But if we observe motion of the midpoint of the rod shown in red color, if we observe this red point not only here, if subsequent motion also, we'll find that motion of the midpoint of the uniform rod will be consistent with the second law. So motion of this particle will follow F is equal to ma, not other particles. Similar way, we'll take another example. As per the Newton law, if no net force is acting on an object, then velocity will be constant. If it rests, it must continue to be at rest. Let's say, so in this case again we take a uniform rod and placed on a smooth horizontal surface, something like surface what we see in case of air hockey. If a sharp impulse J is applied, what is sharp impulse? Something like striking a blow with a hammer or striking a blow with a cue rod, similar to what we have in case of billiards. We apply an impulse, so a large force acts for a short duration, and result of that is an impulse. And after this contact period is over, after the impulse is applied, there is no force acting on the rod. So afterwards, no net force. Then what will be the nature of motion? If you observe this rod, its motion may appear something like this at 3 equal time intervals. So if we look at motion of various particles on the rod, they have complex motion and hence non-uniform velocity. The velocity will not be uniform, and they will have different velocity as well. What we find, though the no net force is acting, the velocity is not uniform. Whereas if we observe the motion of center point of the rod, we observe this point will move in a straight line, and the displacement also in equal time intervals after impulse is applied will be equal. So this point follows Newton's law of motion. So this velocity will be in conformance with the first law, V is equal to impulse by mass of the rod. Another example we take, if again in case of uniform rod, if we just place the rod on a smooth surface and apply the force at the midpoint. In that case, we will find it will have pure translation. All particles will have identical motion and hence same acceleration. So what is special about the midpoint? And this special point is called center of mass of the rod. In case of rod, it is easy to identify as the rod is a symmetrical object. Other objects, it may not be so straightforward. So let's define what is center of mass. What is center of mass for a system of particles or system of mass? It is an imaginary point which follows laws of motion under certain condition. What condition? If entire mass of the system is placed at that point, and if net force or impulse is applied at that point, the motion of that imaginary point would be in conformance with the Newton's law of motion. In other words, a system of mass behaves as if the entire mass is located at that point and resultant of forces acting on the particles is acting at that point. What is the purpose of how it is useful? The concept of center of mass makes the analysis of motion of more complex form of mass systems possible. So it need not necessarily be a point mass or particle-like motion. So a rod motion can be replaced with one point mass, entire mass placed in the center and force acting at this point. So this arrangement is equivalent to this arrangement for the purpose of analysis of motion of center of mass of this rod. So we can reduce a more complex mass system into a simple single particle object. How do you find center of mass? To understand how to find center of mass, we'll first start with the concept of moment of mass. So here we have a particle mass m. Its moment about a reference point. Its moment about a reference point O is product of the mass of the particle and its position vector. So it needs two things. The moment of mass requires two things. It requires a mass and a reference point. Reference point is what we can choose. Reference. So moment of m about O is m into position vector, and this quantity is a vector. So obviously this quantity depends on choice of origin. If we choose the origin where m is placed, if we choose the origin at the point at the same position as m, in that case position vector of m will be a null vector and the moment also will be a null vector, will be a zero magnitude. So choice of origin affects the moment of a mass. How about multiple point system? Take example, we have 3 point masses. What is the sum of moment of mass? I think answer is pretty obvious, logical. Sum of moment of mass is a vector sum of mass of a moment of mass of each particle. Each particle we calculate the moment separately and add it up in form of a vector. What is center mass? Suppose we take example of these 3 particles. So can we find the center mass? Yes, center mass is a special point is the such that, so let's understand definition of center mass. It is if the entire mass m1 plus m2 plus m3 is placed at the center of mass, it becomes a point mass and it will have some moment about O. Its moment will be equal to moment of individual masses. So what we are saying, the moment of entire mass m placed at center of mass will be equal to sum of moment of individual masses. So let's say the position vector is RCM. The center of mass of 3 particle system having this kind of position. It's important, not only mass, position also is important. What is the center of mass? Let's say we replace this one in one particle. What is capital M here? Is m1 plus m2 plus m3. Entire mass is placed at one point and that point, position of that point is RCM. In that case, moment of this is equal to sum of moment of individual particles, and this gives you definition of center of mass. Either we can form its position in vector form, or we can find in form of components. If we take components, actually what this will have x coordinate, y coordinate, and z coordinate. So we can write in component form xcm will be equal to m1 into x1 plus m2 into x2 and so on, divided by the total mass, and similarly ycm. So this is xcm. To find xcm, we'll multiply each mass with its x coordinate and take its summation and divide by sum of the mass. That's how we find xcm, and similar way we find y coordinate of center of mass. Let's begin with simplest arrangement, a 2-point mass system. So there are 2-point masses m1 and m2. This is how they are placed in space. They are at a distance d apart. So first we have to choose a coordinate system, and we should choose a coordinate system which makes the calculation simpler. We could have chosen a coordinate system origin somewhere here. In that case, each particle will have x coordinate as well as y coordinate, which will not make it easy. So best way or better coordinate system would be to choose coordinate system along the line joining these two particles, and I call this line as x-axis. And so this x-axis perpendicular to this would be y-axis. And choice of origin, let me choose the origin also at point m1. What is the advantage of choosing the origin at m1? The moment of one mass becomes equal to 0. And as we will see later, the position of center mass is independent of choice of coordinate system. So I can always choose a coordinate system which makes calculation simpler. What is the coordinate system chosen here? We choose x-axis along the lining joining two particles, and we choose the origin at one of the particles at m1. So that's where my origin is. So both the particles have y coordinates as 0 and z coordinates 0. If y coordinates of each particle and z coordinates are 0, quite obviously ycm and zcm will be 0, which basically means the center of mass will lie on the line joining two points. It will lie only on the x-axis. It cannot lie outside the line joining two particles. That's the first important point. Center mass of two particles will lie on the line joining two points. So let's apply the formula. What is xcm? Xcm will be first mass into its x coordinate, which is 0, and second mass and its x coordinate. X coordinate, the distance is d, hence is the coordinate, this is the positive direction, hence coordinate of m2 is plus d. m2 into plus d divided by sum of the masses, that is xcm. And when you look at this term will always be smaller than 1, hence xcm will always be less than d. So distance of center mass from the origin would be less than the distance of particle m2, which basically means the center of mass cannot lie outside the point joining those two. It has to lie somewhere between the 2 points. Let's see, this is somewhere, so that's where the center of mass is. Its distance from m1 is d1, given by that relationship. What will be d2? We can find the value of d2 by d2 is equal to d minus d1. When we substitute these values, we find this value of d2, and we can find the ratio of distance of center mass from two particles, d1 by d2, and we find d1 by d2 is m2 by m1, which indicates it bears inverse relationship with the mass. So distance of center mass from respective masses are inversely proportional to mass. It is nearer to the heavier mass. So this is, we can clearly see it is inverse relationship. Distance is nearer to heavier mass, which makes sense. If one mass is too heavy compared to other mass, the center of mass will lie almost at the heavier mass itself. For example, if we take example of Earth and Moon, between Earth and Moon there are also like 2 points, and compared to the distance the size is smaller. So there also, since Earth is much heavier in mass, the center of mass lies much closer to Earth. So when we have center of mass, what we have seen earlier, for purpose of analysis of motion, the 2 point masses or more point masses can be replaced with equivalent 1 point mass. So there are 2 masses here, m1 and m2, 2 particles. We can replace this system with a more simpler system, 1 point system. What is the mass? m1 plus m2 placed at center of mass. So I can replace this 2 particle system with 1 particle of mass m1 and m2 placed at center of mass. That's the distance. Now let's understand what is the effect of gravity on point masses connected by a light rigid plastic rod of negligible mass. We have a light rod. This mass is negligible. What does it mean? The mass of the rod is much smaller compared to the point masses. Hence, effect can be neglected. So imagine this is like you could have seen something like a seesaw also. One person sitting here, other person sitting here, and there's a wooden platform, a light platform. The effect of gravity on point masses connected by a light plastic rod. Gravitational force will act on 2 particles like this, as shown in the figure. If m1 is heavier, m1g acting downwards, and we are assuming the center of Earth is vertically downwards. This is how the 2 forces will act. But if I place a knife-like support here, in that case, what I notice, this masses balance. It remains in equilibrium. It means the force applied by the support, the normal reaction here is equal to the weight or gravitational force acting on m1 and m2. Effectively, what is happening, though m1 and m2 are acting on those 2 points, it behaves as if this entire weight is acting at this point. What is this point here? This point in this case coincides with center of mass. I hope I understood. If we place this support here, there is a normal reaction exerted by the support here. It's a point support. So normal reaction, and since these 2 particles are at rest, it is in equilibrium. It means equal and opposite. Forces must be equal and opposite. It means gravitational force must be equal and opposite to this force. Effectively, the gravitational force also must be acting on this point. So what is this? Indirectly, this gives us the definition of center of gravity. What is center of gravity? Is a point where gravitational force appears to be acting. It coincides with center of mass if G is uniform. So if G here at this point and this point are same, in that case center of mass and center of gravity will be same, which is the case in most of the cases unless the object is so large that gravitational G is not uniform. So effectively, what is center of gravity? Center of gravity is the balancing point, and we can define similar to center of mass as the net moment of gravitational force about this point is 0. It's easier to visualize center of gravity than center of mass. Hence, sometimes when G is uniform, you try to visualize center of gravity, and wherever the center of gravity acts, that's the point which will be center of mass as well, as long as G is uniform. So let's take one example. See here, the 2 forks are balanced like this. What is the balance point? This is the point where it is balanced. Now think and tell me, in the previous case, where was the center of gravity? Center of gravity was at the point where the matchstick was in contact with the rim of the glass. That was the center point for 2 forks, and that's the way we can find out center of mass or center of gravity for several shapes. Let's move on. Now, what will happen if we displace 2 point masses? So their point masses m1 and m2. This time, just for the sake of change, we have taken the coordinate system similar, x-axis along the line joining 2 particles. but we have taken the origin at a different point, not coinciding with m1. So two particles are displaced. Initially, when this position, this was the position of center of mass. If two particles are displaced as shown, the first one undergoes displacement of delta x1 and second particle also undergoes displacement of delta x2. So as the position of the two particles change, so will the center of mass. So axiom will also undergo a change. What is happening here? In place of x1, this becomes x1 plus delta x1. So what is the change in this term? The change in this term is m1 into delta x1, and the change in this term is m2 into delta x2. So this change in the numerator will bring about a change in axiom. So what will the change in center of mass? X coordinate. Change in center of mass in x coordinate is change in the numerator divided by the denominator. So delta axiom is equal to m1 into delta x1 plus m2 into delta x2 divided by m1 plus x2. So the center of mass also moves as the particles move. So assume that if we somehow we can create a kind of light bulb which is always located at the center of mass. As we move this mass is here, the light bulb also will move, indicating the motion of center mass. So it has changed. Is it possible to move both the masses without any change in center mass? So what you are saying, is it possible to give some displacement to m1 as well as to m2 and still keep the center mass unchanged? What does the center mass mean unchanged means? Delta Cm has to be equal to 0. So pretty simple question to answer. If there is no change in delta Cm or delta xCm is equal to 0, it means this term must be equal to 0. Then only if the displacements bear this kind of relationship, in that case position of center mass will not change. In that case, ratio of displacement should be equal to minus m2 by m1. What does the minus sign indicate? The direction displacements in opposite direction in inverse proportion of masses. So I need to displace, they have first of all, it has to be in opposite direction. A smaller mass moving by greater distance, larger mass moving by a smaller distance in inverse proportion of masses. In that case, center mass may remain same. So displacement of center mass may not necessarily need to displacement of individual masses doesn't necessarily lead to change in or displacement in center of mass. Let's try and understand of effect of choice of origin. So here in this case, what will happen if we take the origin at m2? So not first we started with here, one case we are taking here. What happens if we take the origin here at m2? What will be position of center mass? So first of all, position vector of center mass, the distance is d2 and this is on the negative side, position of center mass will be equal to minus d2. Actual position remains same, but with reference to this point it will be minus d2. What will happen if this origin is taken at the center mass itself? If I take the origin here at the center mass, then what is the position of the center mass? Center mass will be null vector, magnitude 0, axiom will be 0. In that case, this is a condition, axiom has to be 0, it means numerator also must be equal to 0. So when we take origin at center mass, so it means the moment of all the masses about center of mass must be equal to 0. So with respect to center of mass, the sum of moment of masses is 0. That's another way to define center of mass. So center of mass is a unique and special point such that moment of all masses about that point is equal to 0. In terms of vector form, this is how we can express. Summation of mi ri has to be equal to 0. That's another important property of center of mass. Let's move on to three particle system. So what are three particles? The positions, coordinate system, everything is shown here. So find position vector of center mass, and there are several ways to find center of mass. So you might like to stop this video and try and think of different possible ways of finding center mass, and then restart and see what are the various ways we can find. One way to find center of mass is in terms of vector form. We can find position of each in the vector form. This will be equal to 2a I cap, this will be equal to 2a j cap, this will be equal to minus a j cap, and so on. And we can use the formula and we can find out position vector of center mass, which will give both x coordinate as well as y coordinate. Second method of finding the center mass is we find xcm separately and ycm separately. In that case, what we do to find x coordinate of center mass, first I find out, multiply mass with the x coordinate of each mass and divide by sum of the mass. I can find out xcm and ycm separately. Very similar to previous one. What is third system? Third way is what? First what I do, I find the center mass of these two masses. How do I find the center masses of these two masses? With what I have done before. I can find the center mass, the distance d between them is 3a. Hence the distance of center mass from 2m will be equal to opposite mass m into distance m into 3d divided by sum of the mass 3m. So distance of center mass from 2m will be equal to d, so which will be at the origin. So what is the other way? Replace m and 2m. So first I find center mass of m and 2m and place 3m at their center mass. So I find the center mass of these two, which comes at the origin. So I replace these two masses with one mass placed at center mass. So this 3-particle system becomes now equivalent to 2-particle system. And in this case, pretty simple, both are equal mass, the distance between the 2a, hence center mass will be at the midpoint. So position center mass is a0. So yes, so this approach also has its own advantages. So basically you should have clarity about each of the 3 methods we have mentioned here. One in form of vector form, second in separately x coordinate, y coordinate, and third way is I find first reduce 3-particle system into 2-particle system and then 2 to 1 to find the center mass. That's now center mass for 4-particle system. We'll take a simple system, 4 equal point masses, each of mass m, placed on the vertices of a square of side A. What is the center mass? Any of the system you can choose, as we have discussed in previous slide. And let's try to think of all possible ways of finding position vector of center mass. So let's choose this. Let's again use the third method, what we discussed in the previous slide. First, for mass A and C, these opposite masses. Where will the center mass? Center mass will lie at the midpoint at E. So I can replace these two masses with mass 2m placed at E. Similarly, other mass D and B, these two masses also, I take next system as these two masses, and these two masses also, since they are equal, the center mass will lie at the midpoint, point E. So I can place these two masses also with mass 2m placed at E. So if in all it becomes equal to 4m mass placed at E, only one point placed at E, which will be the center of mass. So entire mass at E, which is my center mass. Actually what you have seen here, this is kind of symmetrical mass arrangement. We can see it is and center of mass will lie at the geometric center. So in this case it was placed symmetrically placed on the vertices of a square. Geometric center of a square is this intersection point of the diagonal. So center mass will lie on the intersection point of the diagonal. So this is true not only in this case, wherever we find symmetrical mass arrangement, like suppose mass is placed on the periphery of a circle uniformly. Is that symmetrical? Yes. Where would the center of mass lie? At the center of the circle. So many such cases, in case of if the mass is distributed over the surface of a circular disc uniformly, again that also symmetrical mass arrangement, the center of mass will lie at the center of the disc. So there are such cases, very easy. Such cases, in case of symmetric shapes, the center mass will lie at the geometric center. Let's take some more case of symmetry. So here masses are placed like this. Now these two masses, what we have done, there is a mass placed at the origin. We have placed two equal and opposite masses, two equal masses at equal and opposite distance. One is plus x distance, another is minus x distance. So both masses are equidistant from y-axis. In that case, the center of mass will lie on y-axis. Reason is pretty simple. Both of them, the moments will be equal and opposite, or net moment will keep becoming 0. So when we find xcm, the net moment, their x component or x coordinates will be equal to 0, hence center mass x coordinate will be 0. Center mass will lie on y axis. As we keep adding equal masses at equal distances on either side of y axis, xcm will remain 0. So if I add some mass here and I add equal mass on the opposite side of y axis, equal mass, then center mass will always remain on y axis. Why? The y axis will act as a axis of symmetry. So how do we state in general terms? If each mass on one side has a corresponding equal mass at same distance from axis on the other side, such mass arrangement can be defined as symmetrical about the axis. And that axis need not be vertical, need not be horizontal. So each mass on one side of the axis has a equal mass on the other side of the axis at equal distance. Such mass arrangement can be called symmetrical about the axis, and center mass will lie on the axis of symmetry. So let's take another example. A uniform ring of radius r has mass m. The mass is uniformly distributed also the periphery of the ring. The total mass is m. And there's another uniform rod of mass m is placed as shown. Just notice this is small m, this is capital M, both are not necessarily equal. But it's placed like this. And if the position of combined center mass is given by the vector ai cap plus b j cap, or coordinate of center mass are ab, then what can we comment about possible values of a and b? What are the possible statements we can make about a and b? So think for a while. What does come to your mind about possible values of a and b? Is range, relationship between a and b, sign, anything? See, as long as we see the masses like this, it's slightly difficult to understand. What we do, we reduce it to simpler mass. This entire circle, this circular mass can be replaced with entire mass placed at its center mass, which is at the origin. So I place this mass at origin, and I replace this mass of the rod also, since it is uniform rod, at its midpoint. This point will be r, this point will be r, midpoint will be r by 2, r by 2. So I place this mass capital M at point r by 2, r by 2. Now it becomes a simpler arrangement. These are the 2 point masses. Now the question is, where would be the center of mass, and what can we say about coordinate of center of mass of these 2 point arrangement? The comments what we can make the center of mass about these 2 point masses are based on what we have seen earlier. Center of mass will lie somewhere on the line joining point 0, 0 with r by 2, r by 2. It will lie somewhere between the two. Hence, x and y coordinates must be equal. So a and b must be equal. So it will lie on this line. Anywhere on this line, x and y coordinate must be equal. And what other comment we can make? The value of the coordinate cannot be, it has to be between the 2 points. So depending on the relative mass, it could be closer to origin or it could be closer to this mass. But it has to be somewhere in between. Its value cannot go on this side, its value cannot go on this side. How do we make the statement? How do we convert into form of mathematical relationship? Range of a or b, it has to be greater than a, 0, but less than r by 2. That's what we can infer about coordinates of center mass for this mass system. Another way to look at this, what is the axis of symmetry? If I draw a line making 45 degree with xy axis, if I draw a bisector, this mass arrangement is symmetrical about that line. So it must lie on that line. That's another way to look at it. So far what we have seen point masses, or what we also call a discrete point arrangement, a discrete mass arrangement. How about continuous mass distribution? So it's something like that. If you take a sheet of metal, mass is distributed over the surface. If you take a thin sheet, it is 2-dimensional mass arrangement. If you take a thin rod of metal, is one-dimensional mass arrangement, and if I take a sphere or any odd shape of metal, wood, or any other object, that would be three-dimensional mass arrangement. So it's a continuous mass distribution. How do we find center mass for continuous mass distribution? We'll not go into many derivation. We'll just go to the basic concept involved in how do we go about finding center mass for continuous mass distribution. So here we take a simple case. A right triangle is cut from a thin uniform sheet of mass per unit area of sigma. Sigma is mass per unit area, which basically means if I take this mass of this shape, if the mass comes to m, if I divide by its area, the ratio will be equal to sigma. If mass is uniform, it means if I take a small area dA, the mass of a small area dA has to be equal to sigma into dA. How do you find? So we'll first focus on finding only the x component, xcm. So first thing what we need to do, we know the formula only for point masses. How do I convert this system into point mass arrangement? How to break this large area into small areas such that each small area could be treated as a point, and it can be treated as a point if x coordinate of that area is known. How do we break into small areas such xcm of each area is known? Here we can divide in such a fashion is cut. Imagine it in your mind or conceptually, we divide this entire triangle, right angle triangle, into several vertical narrow strips. How many such strips? Very infinite number of narrow strips. What is the advantage? So divide into narrow vertical strips, each of width dx. So if we take one narrow strip, do we know the center x coordinate of center mass of this strip? Yes, we do know, because if the distance of this strip is x from the is the distance of the strip is x from the y-axis, all points on the strip, the x coordinate is same. Hence, entire mass of the strip can be placed at one point. So first what we'll do, we find the moment of mass of this narrow strip. We'll pick up one random narrow strip and we add up the moment of all such narrow strips by the process of integration. 3 steps. We divide the area into several small elemental area such that we know the xcm of each elemental area. What is the elemental area here? Narrow vertical strips. Then we pick up one random element. Random element is we take this coordinate to be x, a random value, and we find the moment of mass of that element, and then we add it up through process of integration. Thus how we get the moment of mass of entire triangular shaped area. First we find mass of this small area. The mass will be equal to mass per unit area into area dA. What is area of this strip? Height is h. We can find this height h using similar triangle. H by L will be equal to h by x. Hence area is h into dx. H will be equal to capital H by L into x. Thus mass. Now what will be the moment of this mass? Sum of moment of all elements. This is the moment of one element, and through integration we add all elements. What are the all elements? The leftmost element will have position will have a position of x is equal to 0, and the rightmost element will have a position or coordinate of L. So x is varying from 0 to L. That's the limit. We substitute the all values and integrate. It's a fairly simple integration. We find the sum of moment of all elements as shown here. Once we find the sum of moment, what is the x coordinate of center mass? Sum of the moment divided by the total mass. That's the formula for xcm. So we divide it by total mass. The total mass is mass per unit area into area of the triangle. We find xcm comes equal to 12 by 3. Similar way, we can find out YCM also, and YCM will be from here, from the pointy end. From the pointy end it is 2L by 3, from this end it is L by 3. Similar way, this also along the y-axis also, from the pointy end 2L by 3, from other end 2H by 3, and from this end will be H by 3. So what is the coordinate of center mass here with this coordinate system? It will be 2L by 3 comma H by 3. That's the position of center mass. And the basic concept for all shapes, all continuous mass distribution is same. And if you look at this, this becomes the formula for finding center of mass for one-dimensional mass distribution. Mass is distributed along x-axis. Just imagine this is a sheet of metal, and the way we can roll a piece of paper in form of a cylindrical shape or in form of a thin pipe. So we fold the triangle in form of a thin pipe of length L. So this one, this triangle has been folded in form of a thin pipe, and length is same as this length L. What will be the change in center of mass? Has the position of particles or masses changed? If the position of particles have changed, the position of center mass also will undergo change. Let's understand what has happened to those particles. So let's take again look at what has happened to this narrow strip. This narrow strip has been folded into an element of length dx. The element strip will fold into a pipe of length dx, and all such elements here, which are all such masses which are there on this narrow strip, the x coordinate has not changed. Since the x coordinate of all masses have not changed, the xcm also will not change. The xcm, if you roll this triangle in form of a narrow pipe of length L, the x coordinate of center mass will not change, whereas y coordinate has changed. YCM will change, xcm will not change. So what will be the center mass of this pipe? Yeah, the center mass, x coordinate of center mass will continue to remain same. It will be equal to 2L by 3. So this entire mass has come here, this mass dm here. So the x coordinate of all element of masses will remain same, hence no change in xcm. So what will be the linear? Now it has become a linear mass. It has only one dimension. So what will be the linear mass density of element? Suppose we take this element here, this element has been formed by rolling this strip. The mass of this element is same as the mass of this strip. Length is dx. What will be the linear mass density of the element? Mass of this element divided by length of the element. Mass we have already calculated, sigma into area, sigma into h, which is h by L into x into dx, divided by length dx. This is the term for linear mass density. And if you notice, these three terms are constant, hence linear mass density can be written in form of kx. So linear mass density of the rod will keep varying from 0 to a maximum in a linear fashion. So if we roll a triangular shape, it forms a linear rod of density varying linearly. And center mass, so center mass of the thin rod of length L of linear mass density varying as linear function of x. So what is mass density? In form of kx. Will be same as that of a triangle, hence this rod xcm will be equal to 2L by 3. So indirectly we have found the center mass of a rod whose linear density is varying as linear function of x in form of kx. Now suppose we have a rod which has a linear mass density varying as lambda is equal to lambda naught 1 plus x by L. This term can be written in other form in form of words. It can be written as is varying linearly from x naught to 2x naught, from 0 to L. You notice here at x is equal to 0 it is x naught or lambda naught, At other end, at x is equal to L, it becomes equal to 2 lambda naught. In between, linear variation. How do we define this linear mass density? A linear function varying from lambda naught to 2 lambda naught. How do we get this kind of mass distribution? So suppose I have a sheet which is in form of a trapezium. This height is h, this height is 2h. Again, if this trapezium I fold in form of a thin rod. If I take a sheet which has this shape, uniform sheet, fold in form of a thin rod, its linear mass density will match this. So x coordinate of central mass of this trapezium will be same as x coordinate of central mass of a rod of varying linear density as shown. How do we find the central mass of this trapezium? I can find the central mass of this trapezium by breaking, I don't know the formula for trapezium. So I break this mass into two components such that I know the central mass of each component. What are those two components? One is triangle, another is rectangle. So breaking the trapezium into two components of known central mass. If mass of the triangle is m, since the area of trapezium, area of rectangle is twice as much, this mass will be 2m. So this mass is m, this mass is 2m. And we can replace this entire area with point mass placed at its center of mass. So basically in terms of x coordinate, I place mass m at the center of mass of the triangle, which is 2l by 3, and I take the mass 2m at the center. I place the entire mass of the rectangle at the center mass 2m at a distance l by 2. So these two, x coordinate of central mass is same, which will be equal to, we simply substitute these values, we find the xcm comes equal to 5l by 9, which is same as central mass of this shape. Now we come to another form. What we have here, from a uniform circular lamina, we use the word lamina for thin sheet, two-dimensional shape. A thin sheet is basically two-dimensional object, surface. A uniform circular lamina, a smaller circular part is cut and removed. What is, find the central mass of the remaining part. Find the central mass of the shaded portion. Now this also, do we know the formula? We don't know the formula. So what we do in previous cases, just go to the previous one. What we have done here, we have broken into this area into two components such that we knew the central mass of each, addition of 2. Now let's compare what will happen here. We don't know the central mass of this shape. We break into two masses. Which two masses? This. So what is this shape? This shape is equal to, is equal to this shape minus this shape. Or other words, this plus this is equal to this shape. So let's call this one is full shape. F indicates full shape. What is this one? Part which is removed, MR. What is left is the remaining part, MF minus MR. So I have expressed, one way what I am saying is, I have expressed an area for which, or shape for which I didn't know the central mass, in terms of two mass distributions for which I know the central mass, and this is the difference of this minus this. So unlike previous cases, it was sum of two mass distribution, it is difference of two mass distributions. Two mass distributions, each of known center of mass, each of known mass. So how do you find this in terms of the moment of masses of first two has to be equal to moment of masses of the third system. We will take only the x component. So moment of this mass plus moment of this mass, x coordinate, will be equal to this. So how do we write? Let's assume the central mass x coordinate of this system is xcm. What we have to find? We don't know its value. Mass is known. So what is the moment of this mass? Mass into xcm. What is the moment of this mass? Mass into x coordinate, xr, has to be equal to mass of this arrangement, mf, into x coordinate of central mass, xf. Which quantity is not known? This quantity is not known. So this can be expressed in this form, which becomes the formula or standard way of finding center of mass for this kind of cases, where from a full shape some part has been removed. We know the center of mass of the full shape, we know the center of mass of the removed shape. It could be two-dimensional shape, it could also be three-dimensional shape. What is the formula? Full mass minus the find full mass into x coordinate of the full mass minus the removed mass into x coordinate of removed mass divided by full mass minus the removed mass. I am not calculating the value, rest all is simple substitution. How do we calculate mass of removed part? If I assume this mass to be m, this mass will be equal to 4m. The radius is twice, hence area will be 4 times, mass will be 4 times. I can take this mass of removed part as m, this as 4m, and this will become mf minus will become 3m. Quite easily we can calculate. So this brings us to the end of